Hello and welcome to section 4.5, Indeterminate Forms and L'Hopital's Rule. Okay, today we're going to be looking at L'Hopital's Rule. L'Hopital's Rule is it's a technique we use whenever we encounter a limit of a rational function. Okay, so anytime we have a rational function and the limit of that rational function appears to be an indeterminate form, such as 0 over 0, or infinity over infinity, or some variation of an indeterminate form, then we use what we call L'Hopital's rule, where we differentiate the numerator and the denominator, and then we apply the limit. Okay, so it's basically taking a derivative of the top, derivative of the bottom, and then we apply the limit. Okay, and that's only when we encounter an indeterminate form. So only when we see there's a 0 over 0 case, or infinity over infinity, or some kind of indeterminate form. Okay, so we cannot use it at any particular moment. In any case, it has to be in a case where it's indeterminate when we plug in our limit. Okay, so let's take a look at an example of this. Here we have indeterminate form. When we plug in 1 into this rational function, we end up with natural log of 1 over 1 minus 1. Now, natural log of 1 is 0 over 0. Okay, so here's a good place where we could use L'Hopital's rule. So we take the derivative of the top. Okay, so derivative of the top would be 1 over x. The derivative of x minus 1 will be 1, right? Because we're taking the derivative of x, which is 1. And so we still have limit as x approaches 1. Okay, now plug in our limit. So plug in the 1. So we have 1 over 1, which is equal to 1. Okay, so anytime we encounter an indeterminate form, we take the derivative of numerator and denominator, and then we apply the same limit. Okay, and that will get us our limit problem. Okay, so here we have limit as x approaches infinity of e to the x over x squared. Okay, so if we have e to the x, that would be e to the infinity, which would be infinity. And then we have infinity squared, which will also be infinity. So we have an indeterminate form. So let's see, let's apply L'Hopital's rule. So derivative of e to the x is e to the x. The derivative of 2x, or x squared I should say, is 2x. Okay, so now what happens? So we have e to the x over 2x. Now if we apply our limit, we end up with e to the infinity over 2 times infinity. So again, we have another infinity over infinity case. Okay, but good news, this means we could apply L'Hopital's rule again. Okay, so we take the derivative again of top and bottom. Okay, so we have limit as x approaches infinity. Derivative of e to the x is e to the x. Derivative of 2x is 2. And now we have, well, if we plug in infinity, we get e to the infinity, which will be infinity, over 2. And that'll be just infinity. Okay, and that's okay, obviously. This is not an indeterminate form. We don't have infinity over infinity. Okay, we just have infinity over 2. Okay, and that's okay. So this will be infinity. All right, questions, make sure to ask me in class or you could write me the email. Let's take a look at another example. Okay, calculate the limit as x approaches infinity of natural log of x over the cube root of x. So looking at this problem, if we use L'Hopital's rule, that means we'll have limit as x approaches infinity. This will be 1 over x over, now we have x to the 1/3 on the bottom. If we take the derivative, that'll be 1/3 x and then to the negative 2/3. So that means we would have 1/3 and then x to the negative 2/3 on the bottom. Now what we could do here is we could simplify this. Okay, so we have, let's see, we would have 1 over x. Now the bottom is saying 1/3, and then we have x to the negative 2/3, so that would be x to the better yet, let's write it this way. So we'll say we have 1/3, so that would be 1/3, and then x to the negative 2/3 would be 1 over x to the positive 2/3. So this will be 1 over 3x to the 2/3. Okay, so if we're dividing by that, means we could flip it. So we have 3x to the 2/3 over 1. Okay, and then let's simplify that. So we have x on the bottom, this will be 3/3. Okay, so that means we would have 3, and then 2/3 and 3/3, we could just cross out the 2/3. We'll have x to the 1/3 on the bottom. Okay, so if we do limit as x approaches infinity of 3 over x to the 1/3, okay, and if we plug in infinity here, okay, the cube root of infinity will still be very big, right, infinity. So we have small number 3 over infinity, so the limit of this is going to be 0. Okay, let's take a look at another problem. Find the limit as x approaches 0. Okay, so here, if we do the 0, plug in the 0, we get 0 over 0. Let's do L'Hopital's rule. So that means if we take the derivative of top, derivative of tangent is secant squared, and then derivative of x cubed is 3x squared. Now limit as x approaches 0. Okay, that becomes another case of 0 over 0. Okay, so that means we could take the derivative again. Okay, use L'Hopital's rule again. So limit as x approaches 0. Now, derivative of secant squared, we would use the power rule, right? That would be 2 times secant, and then we would do derivative of secant, which will be, so times derivative of secant is secant tangent. Derivative of 1 is 0. And then derivative of the bottom, 2 times 3x will be 6x. Okay, simplify this a little bit. This will be limit x approaches 0 of 2 secant squared x tangent x. Now if we plug in 0 here, we get another case of 0 over 0. Okay, so that means we'll take another L'Hopital's rule. Limit as x approaches 0. Now, one of the things we have to note is, as we take the limit as x approaches 0, secant squared, limit as x approaches 0, secant squared x, that equals 1. Right? Think about it this way. You have 1 over cosine squared. Right? Cosine of 0 is 1. So you have 1 over 1, which is 1. So this piece is going to turn to 1. Okay, now you have here the 2 and the 6 we could reduce. Okay, that becomes 1/3. So you basically have this case where you have the 2 and the 6 becomes 1/3, and we have secant squared x, and then we have tangent x over x. Okay, so we know that this is 1, and then we have the derivative of tangent x. Okay, so we know that this is 1. And then let's take the derivative of tangent x over x. So that's going to become that's your L'Hopital's rule. So derivative of tangent is secant squared, and derivative of x is 1. And so we end up with, okay, taking the limit as x approaches 0, secant squared, that's going to turn to 1. So we have 1/3 times 1, which is 1/3. Okay. Okay, let's take a look at this one. Now in this one, if we apply L'Hopital's rule just blindly, we won't get infinity over infinity case, right? In the first part, if we plug in, we're going to approach pi from the left, right? The sign, so let's do this. We have limit. So this is a case where we don't have to apply L'Hopital's rule. We can just evaluate. So we're applying pi. We have sine of pi over 1 minus cosine of pi. Now sine of pi is 0. Right, so think sine of 180. And then the denominator, you have 1 minus cosine of pi is -1. You have 0 over 2 then, which ends up giving you 0. Okay, so sometimes you don't have to use L'Hopital's rule. Even though you're given a rational function, you could try to evaluate it at first to see if you get, a regular number. And 0 is perfectly fine. Okay, it's not an indeterminate form. Only when you get an indeterminate form, then you resort to L'Hopital's rule. Okay, let's take a look at example 6. Okay, limit as x approaches 0 from the right of x natural log x. Okay, so in this case, we have an indeterminate product, right? We have x is 0, and then natural log of x as we approach 0 from the left would be undefined. Okay, so we have like a 0 times undefined case, which is an indeterminate form. So this is where we can use L'Hopital's rule. The only problem is we don't see a fraction, right? There's no fraction here. There's no top and bottom. So what we do is we rewrite it as if it's a fraction, right? So we have x approaches 0 from the right. Now the x, we could rewrite that in the denominator as 1 over x. Okay, you become a little creative there, right? Because if you have ln x divided by 1 over x, divided by this fraction is multiplying by its reciprocal, right? So that ends up becoming the same as x times ln x. Okay, and now we could apply L'Hopital's rule here. Right, so we apply L'Hopital's rule. We end up with limit as x approaches 0 from the right. Derivative of the top is 1 over x. Derivative of the bottom would be negative 1 over x squared. Okay, so when we simplify that, we have 1 over x divided by this is times its reciprocal. So times the reciprocal would be like that. And then we simplify a little bit. That'll give us negative x. Okay, so take the limit as x approaches 0 from the right of negative x. Okay, so that means we could plug in 0, which means we end up with 0. Okay, and that's perfectly fine. Okay, let's take a look at this one. Limit as x approaches pi over 2 from its left of secant x minus tangent x. Okay, so anytime we see secant and tangent, we could rewrite it in terms of sine and cosine. Okay, so let's do that first. So secant is 1 over cosine minus tangent is sine over cosine. Okay, which means we could rewrite this as one fraction. So now it turns out into a fraction. So we have 1 minus sine x over cosine x. Okay, and now if we apply L'Hopital's rule, derivative of negative sine would be negative cosine. Derivative of cosine is negative sine. We're applying the limit as x approaches pi over 2 from the left. Now the two negatives cancel. Now derivative of pi, plugging in pi over 2 gives us 0. Plugging in sine of pi over 2 gives us 1. So that gives us an overall limit of 0. Okay, so here we would use natural log to help us. Okay, we'll first set y equal to 1 plus sine of 4x raised to the cotangent x. And then what we will do is apply ln to both sides. So natural log of y equals natural log of 1 plus sine of 4x raised to the cotangent of x. Now, applying the natural log to both sides allows us to write the cotangent exponent as a coefficient in front. Okay, so that's going to come down. So we have natural log of y equals cotangent of x times natural log of 1 plus sine of 4x Now, another way to write this cotangent is we could say this is 1 over the tangent. Okay, so basically we have the natural log of 1 plus sine of 4x over tangent of x. Okay, and we'll do the limit of this as x approaches 0 from the right. So now we could use L'Hopital's rule here. Okay, so we have for the top, the derivative of natural log becomes, well, we would have 1 over this argument, so 1 plus sine of 4x times the derivative of 1 plus sine of 4x, which would be, well, derivative of sine is cosine 4x times derivative of 4x, which is 4. And then the derivative of tangent is secant squared x. Okay, so now remember, taking the limit as x approaches 0 of secant, that turns into 1. Okay, so we basically have 4 cosine of 4x over 1 plus sine of 4x. Because remember, this is equal to 1. Okay, so take the limit as x approaches 0. So we have 4 times cosine of 0, and then 1 plus sine of 4 times 0 is 0. Now sine of 0 is 0, but plus 1. Cosine of 0 is 1. So we end up with 4 over 1, which is just equal to 4. Now, remember that in the beginning we took the natural log to help us with this problem, right? We took natural log of both sides. So what we have to remember in this problem is we have to undo that natural log. Okay? We did the natural log of that function. So we want to undo the natural log by taking a base e. Okay, so basically right now we have natural log of y equals 4. But we want just what y is, right? The limit of y. So we take a base e to both sides, okay? And that'll cancel the e to the natural log. Just gives us the y. So we have e to the 4th. Okay, so the actual answer is e to the 4th. Okay, so just be careful of that. Okay. A lot of people forget that when they're calculating the limit this way. Okay, because you apply natural log, you have to undo it by doing a base e to both sides. Okay, and then e to the 4th will be the final answer. Okay, indeterminate form of type 0 to the 0. Find the limit as x approaches 0 of x to the x. Okay, so we could use the ln apply ln to both sides. Okay, we could say that y equals x to the x. Okay, take natural log of both sides. So natural log of y equals natural log of x to the x. Okay, doing this allows us to write this exponent in front. So we have natural log of y equals x times ln of x. Okay, and now we could apply the limit from here. Okay, so now we did a similar, almost identical problem earlier. Right, so limit as x approaches 0 from the right of x times natural log of x. So remember what we do. We write the x, okay, and we'll put that in the denominator as 1 over x. And now we apply L'Hopital's rule. So we have 1 over x over negative 1 over x squared. Which, when we apply our limit, this becomes 1 over x times negative x squared over 1, which reduces to negative x. And when we plug 0 in there, we end up with 0. Now, only problem with that is, remember in the beginning we took ln of both sides. Right? So basically we're saying here ln of y equals 0. Okay, so now take the base e to both sides. Okay, the base e and the exponent of ln, those cancel. That leaves us with y. And then e to the 0, well, e to the 0 will just give us 1. Okay, and that would be the final answer. Alright, so that's it for the lesson. Any questions at all, make sure to email me or bring it up during the lecture. Have a good day. Have a good night. We'll see you soon.